Welcome to the wonderful world of astronomy. This is chapter 2, Discovering the Universe for Yourself. In this chapter, we're going to look at what we can learn about astronomy, what we can learn about the things up there in the heavens and in the universe just by looking up in the night sky, not with any fancy equipment like telescopes or satellite imaging, but just what we can see, what we discern about the universe by looking up. And this will show you how in ancient times the foundations of modern astronomy were set. So let's start with part 1, Patterns in the Night Sky. As you look at this picture, this is a picture, it's a camera that was pointed towards the North Star, and the North Star is this little bit right there, and the shutter was open of the camera, the shutter was open for many hours. And so what we observe is stars rising in the east and going down in the west, and you can see these star trails, the light over many hours of stars going around. And so we're going to look at why do they do that? Why do the stars seem to go around in a circle? Why do they rise in the east and set in the west? What does the universe look like from Earth? With the naked eye, we can see more than 2,000 stars as well as the Milky Way. Now that depends on where you are, how far away you are from cities and light pollution. That would be in the desert, several thousand stars. And you look at this picture and you can see these faint little dots in the picture. These are stars. And you can see the Milky Way, a stream that goes across the sky. This is a map of constellations. And so any given night, you look up in the sky and you see the fixed pattern of stars that are up in the sky. And at different times of the year and different times of the night, there are different stars, but they all remain in the same fixed pattern. So let's talk about constellations. A constellation is a region of the sky. In ancient times, notably the Greeks, but really cultures all over the world, saw patterns in the stars and they made stories about those patterns. And so, for example, a famous one is Orion the Hunter, and other civilizations in ancient times saw that same pattern, and they saw one civilization saw a warrior, another saw a military general, but the Greeks saw a hunter, Orion, and so they called that Orion. And Orion was out hunting, and it's not shown in this picture, but up and to the right, if this picture showed more of the sky, would be the bull Taurus that Orion is fighting, so they would make a story about that. And Orion is out hunting with his dog. There's Canis Major, the big dog, and his other dog, the little dog, Canis Minor. And so they would make up these stories. Now, in modern times, astronomers are not interested in ancient Greek stories about the sky, but we still recognize the constellations because we take what the Greeks had made these stories out of and we've designated regions of the sky. So the sky has been divided into 88 different regions that are based on the ancient Greeks' stories, their constellations. And so every region of the sky is considered to be a part of some constellation. So while you look at this picture and you see the lines that the illustrator has drawn connecting the dots so you can see the form of a hunter, but anywhere in this red region that designates the constellation Orion, let's say that right where my red pointer is, it's not in the picture of the hunter, but it's still within that red region. And so if astronomers were to discover a galaxy right there where my red pointer is, they could say it's in Orion, and that would give all astronomers who are hearing that an idea of where in the sky it is. So a constellation in modern times is a region of the sky. Usually the stars in a constellation are all very far apart from each other. Their distances from Earth vary greatly. So even though they might look close together, it could be that one is 10 light years away and the other is 100 light years away. They might be very far apart from each other. In chapter 1, in my video on seeing into the past, I showed you two stars, the Gemini stars, Castor and Pollux, And one of them is 33 light years away. The other one is 51 light years away. So they are removed in distance by many light years from each other. They're nowhere near each other. There is what's known as the celestial sphere. Stars at different distances all appear to lie on the celestial sphere. So when you look up, kind of thinking the way people in ancient times did, you look up and you see all the stars, and you can just imagine that they're all painted on a sphere that surrounds the Earth. Well, they're not really painted up there, but that's how we perceive it, like the dome of the sky. And so you can see in this picture, here's a star here, one way out there and there. And when we look up at the sky, we have no depth perception about how far away the stars are. So we just imagine that they're all painted on the celestial sphere, even though because that's how they look, even though we know that they're different distances away. The 88 official constellations cover the entire celestial sphere. And by the way, as we think about the dome of the sky, straight above the North Pole is what's known as the North Celestial Pole, and straight above the South Pole is the South Celestial Pole. In our sky, what this means is when you look in the sky at the North Star is where the Earth's axis of rotation points right up. So it would be where my pointer is right there, much farther away, of course. And so when you look at the North Star, or the North Star, you're also looking at the North Celestial Pole. By the way, also, here's the ecliptic. This is the path that the sun takes around that the sun seems to take around the Earth. Of course, we know that the Earth moves around the sun, but again, we're looking at from the perspective of what does it look like standing on Earth. And this is why people for so long believed in the Earth being the center of the universe, because it looks like the sun and the stars all move around the Earth. So again, the ecliptic is the sun's apparent path through the celestial sphere. And here's the Earth with its equator, and the ecliptic is tilted 23.5 degrees to it. So that's the path that the sun seems to take. As I said before, the North Celestial Pole is directly above the Earth's North Pole, and the South Celestial Pole is directly above Earth's South Pole. The Milky Way, if you're in a dark sky at night, you can see the Milky Way. It's a band of light making a circle around the celestial sphere. It is our view into the plane of our galaxy. So when you see that Milky Way, you're actually seeing billions and billions of stars. You're looking at the thickest, densest part of our galaxy. So if we zoom out, here's an illustration of our galaxy with the galactic plane. And if we are right here at the center, when you're looking into the sky, most directions that you look, you're not looking at the Milky Way. Most directions, you're looking through a pretty thin section of the disk. And so maybe you're looking this way or this way or this way, or maybe down here in one of these directions shown by the white arrow. And so you're looking through a thickness of only a few thousand light years, and so there aren't that many stars. But when you see the Milky Way, you're actually looking in any of these directions shown by the blue arrows. You're looking through the disk of the galaxy where there's a lot more stars and gas and dust. So you're looking through the plane of the galactic disk. When we look at the sky around us, we want to be able to to give some directions of where something is. And so we locate an object in the sky by its altitude and its azimuth. Kind of like we locate things on Earth, they're positioned by latitude and longitude. But this is altitude and azimuth. So let's talk about azimuth first. The azimuth refers to the compass direction. So straight north is an azimuth of 0 degrees, and east is 90, and south is 180, and west is 270, and it divides this ground up into 360-degree circle. And so that gives your azimuth. It's the same compass direction that pilots use, or anybody who's doing any kind of navigation, they use azimuth. That shows what direction to point, to look in. But now, when we're identifying things in the sky, we have to know how high to look, and that's where altitude comes in. So altitude refers to how many degrees above the horizon we can look. And if you're looking directly at the horizon, then you're not tilting your head up any, so you're looking at an altitude of 0 degrees. If you're looking straight up into the sky directly above you, that's an altitude of 90 degrees. And so altitude is going to be something between 0 and 90 degrees. Here's a good vocabulary word for you. Straight above your head at an altitude of 90 degrees is your zenith. Now, when we identify something in the sky, we identify azimuth and altitude. Again, azimuth tells you what direction to face. Altitude tells you how high to look. If something's at your zenith, you look straight up. It doesn't matter what direction you are facing, and so there is no specific azimuth to something that is directly above you. You can face any direction you want. If you look straight up, you're going to see the same thing. Now, another term I'd like you to know is the meridian. The meridian is an imaginary line that starts due north, goes up above the sky through the horizon and down due south. It cuts the sky into two halves, the eastern half and the western half. And so every star, the sun, the planets, the moon, as they rise in the east and go down in the west, there's a point in the day or night when they pass the meridian. And so the sun, for example, passes the meridian at about noontime. It rises on the east, it's in the eastern half of the sky. At about noon, it passes the meridian, and then it's in the western half of the sky. And then if you think about the words AM and PM, AM we think of as morning and PM being afternoon or evening. AM is really from the Latin, it's ante meridiem, meaning before the meridian. So the AM is when the sun, it's before it has crossed the meridian. Then it crosses the meridian about noon, and then we're in PM, which is post-meridian. So again, the meridian is the line passing through the zenith and connecting north and south points on the horizon. Zenith is the point directly overhead. And then there is the horizon. You can think of the horizon as if you're looking straight forward, that's the horizon. We normally think of the horizon as where the land meets the sky, but that can get tricky if you have mountains in the way or buildings or trees. So just think of, if you're looking at a horizon, which is an altitude of 0 degrees, it just means look straight ahead without tilting your head. And the horizon, as it says here, are all the points that are 90 degrees from the zenith, otherwise known as an altitude of 0 degrees. So again, AM ante meridiem from the Latin, the sun's position before the meridian, and PM post meridian, the sun's position after the meridian. Now I've been using degree measures. I said that we divide a circle into 360 degrees. So we can talk about angular positions in the sky. We can also talk about angular size. So the moon is thousands of miles across, but you look at it and you might say it only looks about an inch big, and someone else might say, well, it looks about a foot big. But really, to talk about how big it looks in terms of a distance really doesn't make sense. What we can talk about, what is sensible, is talking about its angular size. If you look at this picture on the left, if you see the moon and it makes an angle as it hits your eyes, there's an angle there. We say it subtends an angle, and it's about 1/2 of a degree. So we talk about the angular sizes of things. We can also talk about the angular distances between 2 points. So the moon is about 1/2 a degree in angular size. So is the sun, by the way. The angular distance, you look at this middle picture, the angular distance between the pointer stars of the Big Dipper is about 5 degrees. So it's about 10 times more than the diameter of the moon. And there's the Southern Cross seen in the southern constellation. The length of it is about 6 degrees. Now, how can we think, how can we discern degrees? What does that mean to me if I'm standing outside? Well, some simple rules of thumb or rules of hand is if you take your fist, like this guy here, hold your hand outstretched, your arm outstretched, then make a fist. The width of your fist from thumb to pinky is about 10 degrees, roughly. So that gives you an idea of angular sizes or angular distances. The width of your fist, 10 degrees. Now you might say, but I have a pretty small hand, or I have a pretty large hand. Well, human bodies are in roughly the same proportions, so that somebody who has a large hand usually has a pretty long arm. Somebody with a small hand usually has a pretty short arm. And so the geometry works out just the same. And again, this is not the most precise thing, but it's a rough estimate that for most people, the width of the fist held at arm's length is about 10 degrees. The width of a single finger is about 1 degree. So now if you take that into consideration and go back to what I said on the left-hand picture with the moon being about 1/2 degree, when you see the moon out, particularly a full moon, hold your arm out and hold your finger up against the moon, and you'll see that the moon is about 1/2 the width of your finger. Now, if you don't have the full moon available right now while you're watching this video, and I'm guessing you probably don't, right now I want you to hold your arm outstretched, just like the guy in the picture. Hold your finger, just one finger, and think the moon is half the width of that finger. And as I'm looking at my finger now, and most people looking at their finger doing this would think, no, I think the moon's bigger than that. I think the moon is bigger than the width of my finger. Well, that might be a bit of an illusion. Actually go outside when there is a moon, a full moon, hold your finger up, and you'll see it is only half the width because it's 1/2 of a degree. Now the other estimate you can see here, if you stretch your hand out from thumb to pinky, that's going to be about 20 degrees. Now, often when we talk about the angular sizes of planets, of stars, maybe the small shifting of stars, we have to talk about angles that are much smaller than a degree. A degree is a very small angle. Remember, it's 1/360th of a circle, but sometimes we need fractions. Sometimes we're talking about hundreds or thousands of degrees. So we need to divide a degree up into smaller slivers. A degree divides up into 60 minutes or 60 arc minutes. So think just like time. We divide hours up into 60 minutes, and each minute is divided up into 60 seconds. Well, angles work the same way. 1 degree is divided up into 60 arc minutes, and each arc minute, is divided up into 60 arc seconds. So an arc second is a very, very tiny angle. And because there are 60 arc seconds in an arc minute and 60 arc minutes in a degree, 60 times 60 is 3,600. So there are 3,600 arc seconds in a degree, just as with time, there are 3,600 seconds in an hour. And that answers this question. The angular size of your finger at arm's length is about 1 degree. How many arc seconds is this? As I just said, 3,600 arc seconds are in a degree. So think about the size of something. Angular size is whatever its physical size is. We could measure that in meters or feet or miles, whatever, times 360 degrees divided by 2 pi times the distance. And so we're not going to be doing this equation, applying this equation in class, but I want to show you what angular size of something is based on. And very often in this class, I will show you an equation. It's going to be very rare that we're actually plugging numbers into an equation, but equations are good in that they show us conceptually how different variables, how different quantities are related. So angular size is the physical size. So hopefully that makes sense to you. The bigger something is, the bigger it's going to look to us. Now, we're dividing by, you can just ignore the 360 and the 2 pi. Those are just constants that make the calculation work out right. Let's focus on the quantities involved. Divided by distance. Dividing by distance means the farther away something is, the smaller its angular size is going to be. So you can have a person standing a short distance away, maybe someone standing right next to you, and they might be an angular size of maybe 90 degrees, 100 degrees, or something like that. But you take that same person who has the same size and move that person down the street a greater distance, and then that person might only look to you like the width of your finger or even smaller. So the person looks to you an angular size. So it is your perception of that person that's based on the person's size, but also the person's distance. Now, the sun and the moon are the same angular size in the sky. They are, you look at them, you shouldn't look at the sun, but the sun and the moon about the same size, or angular size. The sun is actually 400 times larger in diameter than the moon. However, it's also 400 times more distant. And so the 400 times the size and the 400 times the distance, in this equation, they cancel each other out. So the sun and the moon look to be the same angular size. So again, the sun is 400 times farther away than the moon. The sun is also 400 times larger than the moon. So both the sun and the moon have an angular size of about half of a degree. And let's have a good scale of the Earth, Moon, and the Sun. If the Earth is a table tennis ball, the Moon is a marble, and you hold them 4 feet apart, and that is the good scale of the Earth and the Moon. If we're to bring the Sun into this, then the Sun would be a very large ball, about 14 feet wide, and we would have to place it 470 meters away, almost the length of 5 football fields. So think about it from the Earth's perspective. Let's say we're standing at this ping pong ball. We're on Earth. A marble 4 feet away from us will look the same size. It'll have the same angular size as this big beach ball, 14 feet wide, placed 470 meters away. Let's talk about why stars rise and set. They rise in the east, they set in the west, and for millennia, people have assumed that they move around the Earth. Well, here's the Earth, here's the celestial sphere, and the stars, you can imagine, are all on the celestial sphere. Of course, they're really far away, but we imagine them as if they're painted on the sphere, and the Earth is rotating. So the stars are in fixed positions. They don't move relative to the Earth's motion. But as the Earth spins, from our perspective, it looks like the stars are moving around us. And here's the picture from the beginning of this video. As Earth rotates from west to east, the stars appear to circle from east to west. Stars near the north celestial pole are circumpolar and they never set. So if you look towards the north celestial pole at the North Star, the stars immediately around it, they certainly go around the North Star in a circle. In the east they go up, in the west they go down, but they never go down so far as to actually go below the horizon. They just go around in a circle through the course of the night and the course of the year. So those are what's called circumpolar stars. Now, if we live in the northern hemisphere, which we do in America, we cannot see stars near the south celestial pole because they are blocked by the Earth. People in the southern hemisphere can see it, but we in America cannot. All other stars and the sun, the moon, the planets, they rise in the east and they set in the west. What is the arrow pointing to in the photo below? So these are the star trails. They're all going around the North Celestial Pole. So that is the North Celestial Pole. And particularly, it is that bright light is the North Star. It's the star, it's also known as Polaris, that our North Pole, the axis of Earth's rotation points towards. Next topic, why do the constellations we see depend on latitude and time of year? They depend on latitude because your position on Earth determines which constellations remain below the horizon. And they depend on the time of year because Earth's orbit changes the apparent location of the sun among the stars. So latitude, this is elementary school geography here. Hopefully you remember latitude is how far to the north or south you are. So the equator is 0 degrees latitude, and the North Pole is 90 degrees north. The South Pole is 90 degrees south. Longitude refers to, from an arbitrary point, which is in Greenwich, England, how far around east to west you are. So longitude, position east or west of the prime meridian. The prime meridian was just established long ago, and that's what the world just agrees to. That is 0 degrees longitude. It's a certain line. And this is interesting right here. The entrance to the old Royal Greenwich Observatory near London. The line emerging from the door marks the prime meridian. So we have just universally agreed that that line is going to be known as 0 degrees longitude. And if you're to the west of it, as we are, we call it the Western Hemisphere, then you have a west longitude. If you're to the east of it, you're in what we call the Eastern Hemisphere, and you have an east longitude. In Porterville, we're at a latitude of about 35 degrees north and longitude of 119 degrees west. Okay, back to the sky. The sky varies with latitude, but not with longitude. So depending on where you are on the Earth, whether you're up at the North Pole 90 degrees or down the equator or down south, you see certain stars. So where my red pointer is hovering, these are stars that people in the north can see, but people in the south can't see it in the southern hemisphere because the Earth is blocking it. So there's all what we call the northern sky. But then again, if I put my pointer down here, there's a whole lot of stars down here that are in the southern sky. People in the southern hemisphere see those stars throughout the year, throughout the night, but we in the northern hemisphere do not have those stars. So to do astronomy in the northern hemisphere and in the southern hemisphere, you're learning entirely different constellations. Now, the sky, the stars in the sky don't vary with longitude because the Earth just spins around and is just going to see whether stars are over here or over here. That just takes the Earth spinning, and you'd be able to see on one side or the other. Wherever your celestial pole is in the sky, its altitude is equal to your latitude. We in Porterville are at about 35 degrees north latitude, and so the North Star is at a latitude of, or at an altitude in our sky of 35 degrees. Now, if we were standing on the North Pole at a latitude of 90 degrees, we would have to look straight up in order to see the North Star. It would be at an altitude of 90. If we are on the equator, which is a latitude of 0 degrees, we'd look at the horizon, and there would be the North Star. So the North Star is 50 degrees above your horizon due north. Where are you? Well, remember, wherever the North Star is, its altitude, that is your latitude. So you're at a latitude of 50 degrees north. Let's look at these other possible answers. You're on the equator. Nope, the equator has a latitude of 0 degrees, so the North Star would be at an altitude of 0. If you're on the North Pole, you'd be at a latitude of 90 degrees, so the North Star would be at 90 degrees. Longitude of 50 degrees east, you might be there, but longitude doesn't affect where the North Star is. And you're at latitude 50 degrees north, certainly that's true, and longitude 50 degrees east. And again, longitude does not affect this. So that might be true, but doesn't have to be. So in this video, what have we learned? What does the universe look like from Earth? We can see over 2,000 stars and the Milky Way with our naked eyes, and naked eye just means without telescopes or binoculars. and each position on the sky belongs to one of 88 constellations. We can specify the position of an object in the local sky by its altitude above the horizon and its direction, we call that azimuth, along the horizon. Why do stars rise and set? Because of Earth's rotation. Why do the constellations we see depend on latitude and time of year? Your location determines which constellations are hidden by Earth. And that is the end of part 1, Patterns in the Night Sky. Have a great day.